rocket in its launching position. The first great blast starts to lift it, and after gaining initial speed, the first section is cast off at 20 miles up. At 45 miles, the second stage is released. The third stage now fires until it reaches an altitude of 70 miles. At this point, our rocket has now attained a tremendous speed and the motor shuts off. Its forward momentum would carry it straight out into space if it were not for the Earth's gravity. This downward pull of gravity bends the upward course of the rocket into a curved path. And if the rocket's speed going away from the Earth creates enough centrifugal force to balance this pull of gravity, our rocket will continue coasting in its curved path around the Earth indefinitely.
Mr. Lay, is there another way we can illustrate this?
Yes, let's explain it this way. If the rocket were to move at a slower speed, the pull of gravity would soon overcome the rocket's momentum, and it would return to Earth here. If we add a little more speed, the path of the rocket becomes longer, and it goes farther before it returns to Earth here. So, if we have our rocket go fast enough, it will eventually follow a curve which matches the curvature of the Earth and will not fall back. We might say that the rocket falls around the Earth as long as it maintains sufficient speed.
But how does it maintain this speed with the motor shut off?
Remember, our rocket is traveling above the atmosphere in space, where there is no air friction to slow it down.
How fast does it have to go to stay up there?
Now, that depends on how high we want the rocket to be as it circles the Earth. Let's use the altitude of 1,075 miles. Because at this height, the rocket will have to go nearly 16,000 miles per hour and will make a complete trip around the world every 2 hours. A few adjustments in its course will be necessary, but this can be accomplished from the ground by remote control, after which the rocket will continue to coast freely in space forever.
In other words, the rocket will stay up there just like the moon.
Yes, it will circle the globe as a man-made satellite.
What is the purpose of having this satellite up there?
Having this instrument-carrying rocket moving around the Earth will give us a lot of important information which we'll need before we dare let a man make his first trip into space. To run the scientific apparatus contained in the satellite, a mirror will focus the intense rays of the sun onto a silicon battery, converting solar energy into electricity. There will be a television camera to give pictures of the Earth as it appears from 1,075 miles up. We will collect very important data on the effects of the mysterious cosmic rays. Even hits by meteorites the size of a grain of sand will be recorded. Every 2 hours, when the rocket moves over the North Pole, its radio will transmit a stream of data to a receiving station below. This will be the first outpost in man's conquest of space.
One of the big question marks of future space travel will be man himself. How he will react mentally and physically to this unearthly experience is the concern of a new field of science called space medicine. Helping us illustrate this interesting problem is the scientist most noted for his pioneering work in space medicine, Dr. Heinz Haber.
When man steps into his rocket ship and leaves the Earth behind, he must be well equipped to survive in the hostile realm of outer space. To portray the complex problems of space medicine, we have designed a sort of common man. A man just like you and me. We will find out what will happen to him on a trip into space. In a way, he's going to be our space guinea pig. That makes him a brand new biological species. I think we should call him Homo sapiens extraterrestrialis, or spaceman. Since he was picked at random, we cannot tell whether he will be able to tolerate the tremendous stresses to be placed upon him when the rocket ship is fired into space. He gets an inkling of these stresses when he rides in an automobile. When he steps on the accelerator, the car moves forward and he is gently pressed against the back of the seat. His body resists any change of motion. When he comes to a stop, his body tends to move forward. On a test rocket sled, which is pushed forward at tremendous accelerations, the force of inertia is much stronger. We are all familiar with centrifugal force. We duplicate this force in the laboratory by using human centrifuges. These machines artificially create on man the crushing pressure he will have to endure in a rocket takeoff from Earth. His body weight increases until he blacks out and finally loses consciousness. From tests like these, we have learned that man will have to assume a reclining position when his rocket takes off into space. In this attitude, the stresses will be more evenly distributed along his body. He will then be able to tolerate pressures of up to 9 times his weight or more, as it occurs in a rising rocket. When the rocket engine finally stops, man will face his next big problem: weightlessness. Without support, he will be floating freely, drifting, tumbling, and twisting helplessly. In space, a man, a feather, a bubble, or a piece of iron will have the same weight, or rather, no weight at all. However, man is designed to live with gravity, the down-pulling force which Sir Isaac Newton first explained.
Any two bodies attract each other with a force which is proportional to the product of their masses and inversely proportional to the square of the distance between them. Or, what goes up must come down.
Loud alarm signals sound throughout the nervous system whenever we are in danger of falling or stumbling. But weightlessness is not such an unearthly experience. We become weightless for a short while in a dive, on a roller coaster, or in an elevator. But if we remove the support by cutting the cable, we produce the exact feeling of weightlessness in space. It will take iron nerves waiting for the impact that never comes. We can only hope that man in space will eventually get used to this feeling of falling constantly. Without weight, our notions of up and down no longer exist. Man will probably have trouble orienting himself. Confusion such as this is likely to produce nausea. Some people may become victims of a serious form of space sickness. Weightless man in space must learn to guide himself only with his eyes. Beginners can combat dizziness by fixing their eyes upon one single object. The spaceman must learn to move with utmost caution. His muscles are adjusted to normal earthbound gravity. In space, any casual action will be violently magnified. He must coordinate himself under an entirely new set of rules. He can hardly avoid spinning constantly. When he crouches into a compact mass, he will spin faster. If he spreads his arms and legs, the spinning will slow down. After considerable practice, man will be able to master the art of swimming through the air within the rocket ship. For the beginner, a web of ropes might be provided. he must learn that slow, relaxed, careful movements are essential. After his first few encounters with the problems of weightlessness, he will no doubt try to normalize his life. Even the air he breathes will be weightless. Natural circulation of air does not exist, and there is danger of suffocating in one's own exhalations. Air must never be allowed to become stagnant in a spaceship. Circulation must be maintained by constant ventilation. Since all objects are also without weight in a coasting rocket ship, they must be safely secured by bolts and clamps. For handling large, bulky objects, man will have to anchor himself in some fashion. But as it takes force to overcome the object's inertia and set it in motion, it takes equally as much force to stop it once it is moving. On Earth, we are not exposed to dangers from space owing to the protective layer of our atmosphere. But up there, even the hull of the ship would not shield man against the possible hazards of the mysterious cosmic rays. These tiny bullets from the infinity of space will continually penetrate everything. They may prove to be harmful to man. The most energetic of these atomic rays might feel like stings as they shoot through the body. However, there are other bullets in space that may be of still greater concern. Meteorites. These marauders of space travel at speeds up to 150,000 miles per hour. But if one should puncture the walls of the ship, our air supply would rapidly escape through the opening into the vacuum of outer space. Without protection, man could last not more than 15 seconds before losing consciousness. Also, in the intense radiation of the sun, he would soon broil on the one side and freeze on the other. In the void of space, he will have to wear a space suit. This specially designed outfit must be a flexible, airtight unit carrying sufficient oxygen. Featuring built-in all-purpose equipment, it will afford protection and maneuverability outside the ship. Propulsion will be by means of a small portable rocket unit. With proper manipulation of this jet device, even the most subtle movements can be made.
Action, reaction.
Dining under conditions of weightlessness will present new and surprising problems. Liquids will be particularly annoying. They will not pour. They must be transferred by titration tubes. This tube will contain the liquid until it is forced into the desired location. Unless liquids are kept in leak-proof containers, they will escape and float in ball shapes around the cabin, finally coating all surfaces with a wet film. Plastic bottles will be used so that liquids can be squeezed out. Food will be cooked in closed containers by radio frequency short wave. Space etiquette will call for the extensive use of sugar tongs. Man can overindulge in space, but he will never be overweight. To relieve the inevitable tensions of space travel, we must provide suitable recreation. A game of three-dimensional pool could be particularly relaxing. Sleeping will be a new and unique experience. A space traveler will not need a pillow or mattress. His bed will consist of a net enclosure